Hey everybody, welcome to class. Hope that you guys are having a good start to your day. Um, I don't know if anyone had a chance to read my announcement this morning about Top Hat. Like I mentioned the other day in class, we're going to switch from something in the chat. Sorry, just a second. Thanks. Good morning. We are going to be doing polls on Top Hat instead of Zoom. Now, with that said, if anyone doesn't want to download Top Hat or anything like that, or, they prefer to answer the questions like after class or at a later time, that's fine. Do that. What I'm going to be doing with respect to Top Hat is I'm going to be looking at the responses during class. And if you do the questions then, great. You do not have to do the questions that are designated as homework. If, however, you can't make it to class, or it's easier for you to answer the Top Hat questions later on during the day, that's fine as well. They will be open for 24 hours after, or for 24 hours following each class. So right now, the homework Top Hat questions are up, and um, so I just got two conflicting messages, or two messages. One was that I tried to access Top Hat from the Canvas page and it says it isn't connected. Strange. Um, I can, but then, okay, just give me 1 second. I think I know what to do. So, um, with respect to Top Hat, though, in the event that you have if you can't answer the questions during class, that's fine. Don't worry about that. Um, we'll, you can just do the homework ones. Okay. I am recording, so that's good. Then
I need to go somewhere. I'm like, I don't know what to like. Like, where is this?
download the app and okay. So it looks like I got it to work by saying their site can choose a course. No, I'm connected. Lobby. Okay. So it looks like it's working through the app, but not through Canvas. I'll get that sorted out. Making a new account. Okay, I'll get this sorted out. But in the, my point of all of this is that the Top Hat questions are not just during class. So if you don't make it to class, just answer them within 24 hours after. And there's always some kind of minor launch issues, it seems. So I will get this sorted out. I apologize. Okay, start the presentation. My computer is not working currently. Is it possible to do the Top Hat and Zoom from my phone? Yes, it is possible. Um, so, okay, so here's what we got. What I wanted to do today was kind of go over basically like the last three class periods and kind of put it together as one thing. Because we're talking about bonding, and bonding is kind of complicated. It's complicated because you're talking about subatomic particles, but then you're also talking about forming a molecule. So this is kind of it's almost like our mid-session review on this important topic. So the first thing that I wanted you to know about bonding is, and what's very important for you to know about bonding is you need to know the Lewis dot symbols for the main group elements. Now, one of the things that is important to know about this is that I want to take this picture or this screen and translate this to the periodic table. Okay, so here's our periodic table. Drawn out a little bit of a curve, and sorry about that. Okay, so
No, it's okay. I just want to
and now I'm going to change color. That region is group 1 and group 2. This region, or I'm going to go with a different color.
Hello, we're just waiting like a couple.
This region, and let's go with orange. This region is groups 3 through 8. What that means is that this whole block in the middle, which I'm going to switch to a different color, a dark gray, that is not a part of what we're looking at all when it comes to our Lewis dot symbols for main group elements. So we've got group 1, group 2, group 3, 4, 5, 6, 7, and 8. Now, group 1, they have 1 valence electron. Group 2, they have 2. 3 are going to have 3 valence electrons, 4 valence electrons, 5 valence electrons, group 6 valence electrons, group 7 valence electrons, and last but not least are our noble gases. Those all have 8 valence electrons with one exception, and that exception is helium. Helium has only 2 valence electrons. Now, the important thing is these are kind of what we compare everything to. So everything that has 8 valence electrons are noble gases having either 2 or 8 valence electrons. To put it simply, they're happy. They are content. They have the right number of electrons in the right location. Now, what that means for everything else is every single other atom basically wants to get to that same number of valence electrons. So we have 2 different paths that can go. One path is you can gain 8 electrons, or you can gain electrons to get to 8, or you can lose electrons and get to 8 effectively. So if we took, let's say, group 7, fluorine, chlorine, bromine, and iodine, what do you think is simpler for them to pick up 1 electron or to lose 7 and get to 0? It's going to be far easier for them to pick up 1 electron than to lose 7. And whenever I say lose 7, what that means is that if you take lithium being right here on the periodic table, it loses 1 electron, and then it has the same electron configuration as helium. Sodium, what it does is it loses 1 electron, and now it has the same electron configuration as neon. Go ahead and add to the chat. When potassium loses 1 electron, based on what I just shared with you, what electron configuration, what element does potassium then have the same electron configuration as? Lithium loses 1 and goes to He. Sodium loses 1 and goes to Ne. What do you think potassium does? It loses 1 electron, and then what does it go to? Has the same electron configuration as, add the symbol. Argon, you're absolutely right. Okay, Trevor, I think that, yeah, you're on the right path, but it's going back, and so it has to go up 1 row. So you're absolutely right. Okay, now let's take strontium. Strontium has 2 valence electrons. What do you think it's going to do? Do you think that it's going to gain 6 electrons, or is it going to lose 2? Basically, let me phrase that a different way. What is easier, or what? No, let me rephrase that. The noble gases that are nearest strontium, put those into the chat. The noble gases that are nearest strontium. Strontium's right here. What is the noble gas that's before it and what's after it? Great. Kr is 1. What's the one that's after it?
The other.
Xenon. Perfect. Okay. So strontium basically has a choice. That's right, Gabriel. Yeah. Thank you. That's what I thought you were doing, looking at the keyboard there. Strontium can either go here or it can go here, one of those two locations. Now, in order for strontium to go to krypton, it has to lose 2 electrons. To go to xenon, it has to gain 6. Add to the chat, what do you think is easier? Losing or gaining?
Okay.
Losing. And really, this is just a matter of, well, it's easier because there's fewer. Now, if we were to compare that to, let's look at here, I got to clear all my drawings. Well, not all of them, because I got some good ones there. Let's look at oxygen. What does oxygen want to do? It's got 6 valence electrons. Let's first go with what are the noble gases that come before and follow oxygen? Add those to the chat if you can easily. Helium, yep, that's the one that comes before it. What's the one that follows it? Neon. Okay. So when we look at these two, helium's got 2 valence electrons, and neon has 8. If oxygen were to lose electrons, well, it would lose one, and then it would get to nitrogen's electron configuration. Then it would lose another, go to carbon, another, go to boron, another, go to beryllium, another, go to lithium, and then finally, it would lose those 6, and then it would get down to the electron configuration of helium. Let's see, that would be a total of 6 steps, basically. Or oxygen can gain 1 and then a second electron. And then it has 8 valence electrons. So you can kind of look at this and say, okay, well, fluorine wants to gain 1 electron. Oxygen can easily gain 2 electrons and get to that noble gas configuration. Things that are on the right-hand side of the periodic table, for the most part, they find it easiest to gain electrons compared to losing electrons. Now, with that in mind, what we've got here is basically the foundation for our octet rule. Atoms tend to gain, lose, or curveball here, share electrons until they have 8 valence electrons. That's kind of your goal, 8 valence electrons. This, I think, captures it really well. Things on the left-hand side tend to lose electrons, and things on the right-hand side tend to gain electrons. There are some that are a little bit tricky. For instance, those group 3 elements, boron and aluminum, they're different. Aluminum likes to lose 3 electrons. Boron, well, it likes to share 3 electrons. So there is some gray area, but when it comes to groups 5, 6, and 7, or actually when it comes to groups 1, 2, 5, 6, and 7, these statements here and here are totally true. Now, clear all my drawings. We've got our first question. I've got a minute and 30 seconds accounted for this question. If you have the app, participate. If you do not, and Canvas isn't working, well, I'm going to look into that. You can just go ahead and do this one as the homework question. So what is the charge of oxygen when it has a complete octet? Think about what it's gaining and how many of it it's gaining. There's about 30 seconds left.
I took some notes on that, so we can keep working on that now. I'll of course send out the feedback. I mean, then all the afterwards. Terry, do you want to ask me something?
All right. The most popular answer was -2, and that's absolutely right. Because what is oxygen doing? It's picking up 2 electrons because it brings in 6 valence electrons. To get to 8, it has to pick up 2 more. And what is the charge of an electron? It's minus. So it has a -2 charge. Great job. Okay. Now,
Yeah.
when we talked about sodium and chloride, the same thing was kind of true. We had a sodium atom or an ion. The sodium atom has 11 protons. It has 11 electrons. What sodium loves to do as a group, I'm going to label it as G1 element, is it loves to lose an electron. Okay, so now this is kind of an accounting exercise. A sodium ion. This is an ion, this is an atom. This is an atom. The sodium ion still has 11 protons, but it's lost 1 electron, so it only has 10 of them. So it has a +1 charge. A chlorine atom has 17 protons, 17 electrons. Well, chlorine, as a group 7 element, what can it do? It can gain 1 electron to get to a -1 charge and a complete octet, giving it a total of 18 electrons. Now, this chlorine ion that I mentioned, add to the chat if you remember what the appropriate name for that is. And think about NaCl. Think about times that you've said NaCl, table salt, and using the chemical name of table salt. What is Cl minus? What's the appropriate word for that? Spoiler, it's not chlorine, it's chloride. Absolutely right. So chloride. So Cl minus. Okay. Now, that's what we've got going on there. We've got sodium ions or a sodium ion that forms by losing an electron. And lo and behold, chlorine's there to accept that electron. Now, this table shows clear all my drawings, our most common ions. One of the things that I was saying a little bit ago was that we've got aluminum, that's kind of an oddball. It likes to lose 3 electrons, and it gets to the noble gas configuration of this guy right here. Fluorine, oxygen, nitrogen. They love to gain 3, 2, and 1 electrons respectively to get to this noble gas configuration. The entire idea of what different elements do is they like to gain or lose electrons. And gaining and losing electrons, when they do that, they are trying to basically get to a noble gas electron configuration. So that's the important part of basically everything in terms of bonding. Are you gaining or losing electrons to get to a noble gas configuration? Now, another part of this is when something gains or loses an electron. What's the appropriate name or what's the right name to call it? When we talk about, um, when we talk about metals in group 1 and group 2 of the periodic table, they like to form ions. And they like to form ions that are named after themselves. For example, a lithium ion, a sodium ion, potassium, magnesium, and calcium ion. That is all that there is to say about that name. Whenever it comes to your non-metals, which I'm going to switch my color. I'm going to go to green. Your nonmetals are right here. Your nonmetals, they like to have something added to them. You take the name of that compound, of that molecule, or that atom, I'm sorry, and then you end the name with IDE and the word ion. For example, the sulfide ion. That is S2 minus. Sulfur likes to gain 2 electrons to get to a noble gas electron configuration and have a complete octet. Nitride. How many electrons does nitrogen like to pick up to form an ion? Nitrogen is a group 5 element. So it's trying to get to 8. So 5 to 6 is 1. 6 to 7 is 2. 7 to 8 is a third. So nitrogen likes to pick up 3 electrons, giving it an N3 minus charge. Now, taking this into consideration, here's a question. The compound Na3N is best known as A, trisodium nitride, sodium nitride, monosodium trinitrogen, trisodium trinitrogen. Okay, so let's break this down and we'll work through this together. So if you haven't answered it, don't answer it unless you know the answer. So we have 3 sodiums, 1 nitrogen. This is an ionic compound. This ionic compound forms between a metal, sodium, and a nonmetal, nitrogen. So these 2 different things gained and lost electrons. So if we were to say nitrogen, it's a group 5 element. So how many electrons does it like to pick up? And if you're on camera, you can show fingers, or if you're not, add it to the chat. How many electrons does a group 5 element like to pick up or like to gain? 3. You're absolutely right. Because when it is group 5, it wants to get to group 8. Okay, so would it be fair to say that this is 3 minus? I can add more time to the, there we go. N3 minus, okay? Sodium, Na, the sodium ion. It likes to, as a metal, it likes to form a cation. So it likes to lose electrons. It's a group 1 element. So how many electrons does it like to lose? Add that to the chat.
It's related to this one. Does anybody else have
Group 1s love to lose 1 electron. When you lose 1 electron, you're going to have a +1 charge. So let's say you got one thing that is +1. What's that called? That's simply the sodium ion. N3 minus, is that a nitrogen atom? No, it's not. Given these options, it's not going to be trinitrogen. So those are out. So we're really looking at sodium nitride. B as being our best answer. So let's see what the responses were to this question. Clear all my drawings. Okay. Awesome, guys. So the folks who answered trisodium nitride, you fell for the trap. And I'm sorry, I don't mean that as, yeah, didn't mean to trap you. But use the tri prefix whenever we're talking about a ionic compound. we don't need to use that prefix. The prefixes are reserved for covalent compounds. So whenever you see something like NaN3 or NaCl or MgCl2, think about, okay, well, that's a metal and a nonmetal. Whenever you have that nonmetal and a metal come together, you do not need to have the prefixes there. Carbon monoxide, that's two nonmetals. Carbon dioxide, that's two nonmetals. Okay, so great job, everyone. All right. Now, naming ionic compounds, one of the biggest things is remembering that IDE suffix because FeCl3, if we took something like that, what we're talking about is that's called iron 3 fluoride. Did we have to say trichloride? No, we didn't, because it's an ionic compound. So ionic compounds did not use the prefixes. Covalent compounds do. Here, what we had was lead 3, 2, and 4 oxide. Those are different lead ions. The reason, or whenever we use this 2, 3, or 4, well, that's because lead, or Pb, is a transition metal. And whenever you see that +2, +3, +4, that's going to indicate this is a +2 ion, this is a +3, and this is a +4 ion.
Oh, yeah.
So this brings us to bonding. So we've been talking about things forming an ion or not an ion. And here what we have is, sorry about that, things that are going to either be an ionic compound or a covalent compound. Ionic bonds, you're giving up an electron. Covalent bonds, you are sharing electrons. Sometimes bonds can be displayed, covalent bonds can be single, double, or triple bonds. Each one of these lines right here corresponds to two shared electrons. So when you see two bonds, that's four shared electrons. This would be six shared electrons. So with that in mind, whenever you look at something like nitrogen right here, that nitrogen has six electrons around it. Does it have a complete octet? Not yet, but one, two. Now it's got a complete octet because it has those two additional electrons. Now, when it comes to sharing electrons, we have different species that have basically a different appeal or a different draw for these electrons. That's known as electron affinity. It's the ability of an atom to attract shared electrons. Our most electronegative element is none other than fluorine. Our least electronegative, francium. So when it comes to francium in sharing electrons, francium wants nothing to do with any electrons. It doesn't want to share them at all. It will give you the electrons. They're yours. Keep them. Bond polarity. That sharing is not always 50-50. That sharing can be, well, in the case of ionic bonds, well, you have an electronegativity difference that's greater than 2. Now, this brings up our next question. Which bond is most polar? And before you answer this question, let me write some things on the screen. Okay, so I'm going to add some time. And before you answer your question, I want you to know that carbon has an electronegativity of 2.5. Fluorine is 4.0. Hydrogen is approximately 2.1. And bromine, I think, is like 3.6. So which of these bonds is most polar? And when we're talking about and curious about bond polarity, What we're looking for is how different those electronegativities are. Okay, we've got about a minute left on this question. Now, just my thoughts on this question is the calculations part of this. I think everyone knows how to do this pretty well, but it's almost like, and this is one of the big challenges in a chemistry class, is it's almost like you're learning another language because you're trying to apply what does polarity mean? Non-polar. What are those differences? Electronegativity, what does that mean? And so we're working on getting that terminology correct because most polar bond, that's going to be the greatest electronegativity difference. And if you have those values up there, it's I think that it's pretty easy to see when you subtract 2.5 and 2.1, the difference is 0.4. 3.6 and 2.5 is 1.1. And then whenever you get to 4.0 and 2.5, you can see that that's your greatest value. That's your greatest difference. So that's all that you're doing for this sort of question. Now, when it comes to, so a covalent bond can be a polar bond. When it comes to numbers of bonds that each element is going to form, these things sort of trend with what we've previously talked about. Well, how many electrons does fluorine want to get? It wants to get one electron. How many bonds therefore, how many electrons does it want to share? Well, if it's sharing one, then it's getting its extra electron. Oxygen likes to share or likes to get two more electrons. How can it get those? By sharing. Nitrogen likes to get three electrons. It can get those by sharing. Carbon and silicon, they each have four valence electrons. So if somebody comes around and is like, hey, I'll share an electron with you, it needs four things to share those electrons. So four hydrogens to make a molecule like CH4. Now, naming of covalent compounds, this is where we get into prefixes. Carbon monoxide, carbon dioxide. That's where this is very important, knowing the different prefixes in order to come up with the actual names. Now, this list I previously mentioned, I don't expect you to memorize this or anything of that nature, but I want you to know that these substances can be used to make compounds. For instance, if we have a nitrate ion, there is a compound known as NaNO3. What is Na? Add that to the chat. Okay, sodium. I like it. What's NO3? Minus. Well, first of all, it's an ion. The appropriate name for it is the nitrate ion. So what's NaNO3 when you put those two things together? Sodium nitrate. Absolutely. I know that I've seen this in the past where someone will say, oh, it's sodium nitrate ion. You don't need to include ion anymore because sodium effectively cancels out the charges. So then NaMNO4. What's that compound called? Sodium, you're close on the magnesium. MnO4, sodium permanganate. Perfect. Great job, Caitlin. So you have to look at, well, what is this formula? So Mn is the element manganese. O4, oh man, this whole thing makes what's known as the permanganate ion. So sodium permanganate. Did we have any prefix? Did we call this monosodium? No, we didn't, because it's not a covalent compound. It's an ionic compound. Um, K2SO4 would be, well, there's two potassiums. We don't care that there's two potassiums. It's potassium, and then SO4. We'd have to find this on the chart. Well, potassium sulfate. Will you have questions on your exam about this with this chart present? You will. Will there, will 100% of folks get these questions right? 100% is tough to come by. But I want you to look at this and be like, oh, this chart is going to be there. That's a good reference. I need to use that good reference. So whenever you see these things, be thoughtful of that. Like ammonium, NH4 plus. Why won't we need to acknowledge the two next to the potassium? That's a great question. And that goes back to, so this is the rationale for this is that potassium is a metal, and metals love to form cations, positively charged ions. SO4 is a negatively charged ion, and it has a 2 minus charge. And this is kind of like um, everyone knows, every chemist knows that sulfate is arranged where it has a 2 negative charge. So whenever you pair anything up with SO4, you know that that compound is going to have a 0 overall charge. So it would be K2SO4. It's kind of like, well, how many potassiums were needed to form potassium sulfate? Well, two, but that's because potassium has a +1 charge. In the same hand, in the same way, if you were to say Ca, calcium is a group 2 ion, and it likes to form a Ca2 plus. So CaSO4 is calcium sulfate. You just call it calcium sulfate because it's kind of implied that it's forming a 2 plus ion. Does that make sense, Kevin? Okay, cool. And yeah. So this is all kind of these are sorts of questions that you should expect to see um, with this material. Like I said, I will give you a question on the exam that basically gives you this chart. It says, what's the name of this compound? Or here's the name of the compound, select the right formula. So then what you need to know is you need to be able to identify, oh, is this a covalent compound or is this an ionic compound? And anytime you're dealing with, and I'm pointing over to my left because that's where my screen is, anytime that you're dealing with anything on here, it's an ionic compound. Now, one place where people get tripped up and they fall for, or they know the answers. They see ammonium, NH4 plus, and they are asked for what's ammonium? What is the formula for ammonium dichromate? Okay, ammonium dichromate. Here's where it gets a little bit tricky. Dichromate has a charge of 2 minus. So we've got Cr2O7. I'm not going to write the charge there. What instead I'm going to do is I'm going to balance it out with NH4. Okay, NH4 rolls in with a plus 1, Cr2 is -2. If I combined one NH4 and Cr2O7, the charge of that would be 1 minus because of the fact that Cr2O7 has a -1 charge, NH4 has a +1 charge. So add to the chat, how many NH4s do I need to make ammonium dichromate to give it an overall 0 charge? Because dichromate is -2, ammonium is +1. How many ammoniums do I need? How about 2? Absolutely. I got a private message of 2. You're absolutely right. So we need 2 of these. Okay. Now I'm going to do some erasing. How many have I written? Right here. If you read that, I think you'd look at it and you'd be like, oh, okay, there's one NH4. So that's a single ammonium. How would I want to display that I've got 2 there? What does that look like? Does that look like I have 2 NH4s, or does that look like I have a compound that is NH42? Yeah, it looks a little bit like NH42 or NH42. That's not what I want to say. And what would be a problem is if then you were like, oh well, I'll write it as a subscript. Well, that just looks like I have bad handwriting because to be honest with you, and to just among the 55 of us, I do have bad handwriting. If I wanted to say that there are 2 ammoniums, what I'm going to do is put ammonium, NH4, in parentheses, and then put the 2 outside the parentheses. That shows that I've got 2 of whatever is in that parentheses. So essentially, it's like this. 2 + 1 charges, which will cancel out the charge of that -2. So that would be the formula for ammonium dichromate. NH4 parentheses 2 Cr2O7. Okay. All right. Well, does anyone have any questions? Why it would need? Absolutely. Okay, let me go ahead. I'm going to clear all my drawings off of here. So ammonium dichromate. Ammonium is NH4 plus. Dichromate is Cr2O7 2 minus. Whenever we're naming a compound, we want it to be electronically neutral, to have a 0 charge. Now, if we had, I'm just going to draw ammonium as a circle with a positive, and then dichromate as minus, minus. Okay, so if we had 1 ammonium, that would basically cancel out one of the negative charges on the dichromate. So ammonium dichromate, well, that would be NH4, a single one of them, canceling out one negative of dichromate. So that would give me a molecule, NH4 Cr2O7 minus 1. That's a compound that has a -1 charge. That's not what I'm looking for. What I'm looking for is something that is electronically neutral, so it has a 0 charge. So essentially what I'd need to do is cancel out this other negative. How would I do that? Well, I'd need another positive. So truly what I need to make ammonium dichromate is 2 ammoniums. If each one of these positive charges is an ammonium, I need 2 of them to cancel out the negatives of dichromate. Does that help?
Yes, thank you.
Absolutely. So that right there is one of the important things about writing an ionic compound. You want it to be electronically neutral. You want it to have a 0 charge. So However you, however many of a different thing that you need, you're going to have to write that in. So if we took sodium phosphate, okay, this is an ionic compound because we've got a phosphate ion and the metal sodium. Sodium is a group one metal and it likes to form Na plus. Phosphate is PO4 3 minus. Add to the chat what you think the formula for sodium phosphate would be. With how many sodiums would you need to get you a molecule that has a zero overall charge? Caitlin, that's Na3. Caitlin, Trevor, awesome. The only thing, yes, awesome. I got a private message of Na3PO4. That's absolutely right, y'all. The only thing is you don't need to, after you've written Na3PO4, well, it doesn't have an overall charge because you got those three sodiums that cancel out the negative, or three positive sodiums that cancel out that -3 charge on the phosphate. So great job, everyone. This is like tricky and yeah, it's tough wrapping your mind around it. Okay, well, I am going to go ahead and stop my recording. If anyone has any more questions, I'm glad to hang around for a little bit though.